holidays, maybe. So, did you guys, relax over the, holidays? All right. So you're ready to get more linear programming stuff, I suppose, right? Okay, so I guess a couple of things I want to tell you. First is the second assignment is online. It's on my learning space. So there will be 3 questions. So you probably want to start as soon as possible. And yeah, and second, the final exam date is on August 9th. Okay, so the bad news is kind of late. The good news is you have plenty of time to study, right? So, no excuse. Say I don't have time. Now you have a lot of time. Okay, so now I want to start with the linear programming modeling examples. So this is probably the most important technique or important skill you can learn in linear programming. So how do you model a business problem? How do you formulate an LP for a business scenario, right? So today we are going to go through a few examples, and hopefully that's going to give you some practice. And later on, if you see another problem, which is probably you have not seen that before, hopefully you can learn some skill and some typical techniques. All right. And I'm assuming that you guys have checked out those examples by yourself already. Okay, so for each problem, I probably will give you only 1 or 2 minutes before we work on that together. So the few examples we have here, all of them are from the textbook. Okay, so you can refer to your textbook. So the first question is that there's a petroleum company, right, which produces 3 grades of oil: super, premium, and extra, from 3 components. And you want to find out how do you mix those components, okay, to produce the 3 types of oil so that you can maximize profit. Okay. So you have 3 components, and they have availability constraint per day, and that's the cost per barrel, right? And then you want to blend those components into 3 types of oil, and you have 3 possible grades, and for each grade there are specifications. Right? For example, to produce super oil, you want to have at least 50% of component 1, but not more than 30% of component 2. Okay? So I guess those are technical constraints, right? I mean technical specifications. Sorry. All right, and for each type of each grade of oil, there is a selling price. So 23 here, 20, and 18 there. Okay. And so basically you want to blend 3 types of components, 3 components into 3 types of oils, right? And this is a typical blending problem. Typical blending problems. Okay. So you can define decision variables this way. So Xij, so let me see if we have so Xij is what? That is, for example, this is X2P, right? So that is the amount of component 2 in Premiere oil, right? So that is the amount, okay? So you can define Xij this way. So I is the component, J is the type of, the grade of oils, okay? You have those, then you have non-decision variables, right? Once that is done, then you can kind of write down those constraints. For example, in the super type of oil, right? You will have at least 50% of component 1. So based on our decision variables, right? So here is the super grade of oil. You have X1S, X2S, X3S. Okay, so those are the 3 components in this grade. And then this is the total amount of super oil you produce, right? So when we say blend, that means the weight will be just the summation of the components, right? It's a blend problem. So if you decide X1S, X2S, X3S, those 3 components, then that is the total amount of super oil you produce, right? And here says at least 50% of component 1, that means component 1, X1S, divided by the total, right, is 50% or more, right? So that's why we have this constraint. Now, in linear programming, we want all the constraints to be linear, right? And actually further, we want to move all the decision variables to the right-hand side, to the left-hand side, and all the numbers to the right-hand side, if possible. Okay. So from here, we can write this, right? X1S is larger than or equal to 0.5 times this, 0.5 times that, 0.5 times that, right? And you can further simplify this constraint. Okay, so you move everything to the left, and you have this. So at the end of the day, you can write down this constraint in this way, right? So that is the constraint for this specification. Okay. Now, no more than 30% of number 2, right? That means X2S, right, divided by the total is less than or equal to 30%. Then you can do the same thing. You can simplify the constraints, right? So does it make sense? So by doing this, you can have all the constraints there, right? And of course, all those decision variables have to be more than, have to be non-negative, right? So those are the constraints based on the blending kind of specifications, right? Then we have some other constraints like, the amount of component 1 is no more than 4,500 barrels, right? So that's why we have this constraint. The amount of component 2 per day is no more than 2,700 barrels, and so on. Okay, so those are the component availability constraints, right? And also it says that you want to produce 3,000 barrels of each grade of oil. So X1S, X2S, X3S. This is the amount of super grade of oil, which has to be 3,000 or more, right? So that's how we write all the constraints. Any questions on the constraints? Good. Now we also have to write down the objective function, right? Objective function. So objective function, of course, is like revenue minus cost, right? Revenue minus cost. The revenue, of course, is from selling those 3 grades of oil. the cost, of course, is the cost of the three components, right? So there are different ways to write it. But as I said, of course, after class, I'm going to post those writings, those things on learning space, so you don't have to copy them down. Okay. So we are talking about how to write down the profit functions. Okay. There are more than one way to do that, but one way to do that is we can figure out what is the profit from the grade of super. Right. If you look at the very top, I can write the profit from super grade of oil in that way. And the reason is, so if I, here says, okay, 23, right? So I want to write something here probably, just here. Okay, so the super oil is 23, right? So that is the selling price, that is the revenue. This is 20 and this is 18, right? So those are the revenues. In terms of cost, this is 12, this is 10, this is 14. So if we want to, if we just want to look at the super grade, right? The revenue would be 23 times this plus that. So this is the total amount of grade super you can sell, right? So 23 times the sum minus the cost of the three components. So that would be 12 times x1s, 10 times x2s, 14 times x3s. Okay. So that's why we have the profit function at the very top. Okay. Does it make sense? And of course, you can write the profit from extra, the grade of extra, right? So for the grade of extra, that would be the 18, the selling price, times the sum of those three things, right? Minus 12 times this component, 10 times this component, 14 times x3e, right? So you can write the profit functions for all three grades of oil, right? So the total profit would be the profit from the three grades of oil, right? And of course, you can do some simplifications, and you will have this objective function. So this objective function involves some work. So you have to go through some processes before you can get the final answer over there. Okay, and of course, we always want to say, you don't want to forget to write this. So any questions about this blank example? All right, I'll take that as a no. And the second example is something called the product mix. So you have different types of products, similar products you can produce, okay? And what is the optimal mix, right? Okay, so if I look at here, we are saying that there's a company called Quick Screen Shirts, and it produces like 4 shirts, t-shirts, front or back and front, 2 types of sweatshirts, front and back and front, right? So 4 types of shirts. How much produce for each type of shirt, right? That is the question. And it involves some constraints, like you have to finish everything within 72 hours, right? Maybe maybe after game, right? You need to get your shirts available right away, right? I mean, within 72 hours. You also have a tracking capacity constraint, right? You only can ship 500 standard boxes, right? And standard box can hold 12 t-shirts. Okay, and if you want to ship the sweatshirts, then you need a bigger box, or you need 3 standard boxes to ship 12 sweatshirts. Okay? And you also have the financial constraint. You can only spend $25,000. Okay, and also like the raw materials, right? You only have 500 t-shirts. You have 500 dozen blank sweatshirts in stock. Okay, so. Okay, so obviously in this problem setting, we are interested in making everything dozens, right? We don't want to do individual because making everything dozen make sense, right? All right, so this is a picture, and these are some of the data, right? So you have 4 types of shirts, right? In terms of processing time, so. For example, t-shirt front takes 1.08 hour to produce, and the cost to produce it is 25, and the profit is 45. Okay? So here is per dozen. Okay, this is the cost. This is the profit. So the profit is given to you for each type of shirt, right? So you don't have to calculate what is the profit margin for sweatshirt, front, is given to you, right? So that's good news. So as we said, product mix problem. Basically, you want to decide how many units of each specific product to produce, right? And so you have x1 to x4. And objective function, that is the profit for x1. X1 is the sweatshirts from printing. So that the profit is 90, right? So before I forgot, of course, x1 is the dozens of sweatshirts from printing you want to produce. Okay, so as we said, it's kind of important to make everything, make the units consistent, right? So just in case you forgot, so everything is in terms of dozens, right? In terms of dozens. So you have the profit function, right? And you have the time constraint. You have to do everything within 72 hours, right? So you have this constraint. So you also have the shipping constraint because you have a shipping capacity constraint, right? So here says we only have 1,200 boxes, right? 1,200 boxes. So a standard box can hold 1 dozen t-shirts, right? So what are the t-shirts? So t-shirts are x3, x4, right? So this is the number of dozens of t-shirts from printing you want to produce, right? Then you have x1 dozens of t-shirts. They need x3. You have x3 dozens of t-shirts, right? So you need x3 boxes. So you need x3 boxes, you need x4 boxes. Now x1, x2, they are about sweatshirts, right? As we said, 1 dozen sweatshirts need 3 standard boxes, right? So you want to produce x1, you want to ship x1 dozens of sweatshirts, you need 3 x1 boxes. Okay? So that's why those are the number of boxes we need has to be less than equal to 1,200. And the next one is the cost of financial constraint, right? And then we are saying that we have 500 dozen blank t-shirts, okay? We have 500 dozen blank sweatshirts, okay? So, I mean, this is a little bit confusing, right? You may think that, the t-shirts plus thresholds combined is 500 or less. You know, that's okay, but here, you know, it's a little bit confusing, but let's assume we are saying that we have 500,000 blank t-shirts. We also have 500,000 blank thresholds, right? And that's why we have these constraints, those two constraints, right? Those two constraints, and as we said before, we want this two. This is the non-negativity constraint, right? So our job is done, right? So that is the LP formulation, right? Next step of course is to solve it using Excel solver, right? Doesn't mean yes.
So for this class, we're dealing with like linear programming with like different components and blending. So in the exam, like we just have to leave it like at this point, like find the Poisson function and the constraints, and that's it.
Quite likely, yes.
Yeah, and okay.
Unless it's a very simple LP problem, you
That
can solve it.
that'd be great.
Yeah, that's
Or,
right.
yeah.
That's right. Good question. Okay, so this is another example. So how about you guys take like 1 minute, maybe 2 minutes to check it out, okay? And I'm assuming you guys, not all of you guys have tried yourself yet, right? Am I right? Okay, 2 minutes. Have you tried? So
be honest, I don't get it. No, I'm looking at what you did right now to figure it out.
Okay. So this one is not that obvious. Okay. Okay, so you have like regular capacity, which is 160 computers per week. You also have overtime capacity, which is 50 computers per week, I suppose. You also have the capacity and the cost, right? Regular time cost is 190 pounds or whatever. Overtime cost of a computer is 260, right? Which makes sense, of course. Overtime is more expensive, and also the cost it will cost you $10 per computer per week. You know, just to hold it in the inventory for future delivery. You want to meet all the orders, okay? So those are the demands. You want to meet all of them, and you know, basically you want to make sure you have 105 computers at least, so you can meet this demand, right? So of course you want to minimize the cost, but you want to find out how much regular production you need, and how much overtime production you need, right? And you want no inventory left over at the end of the week 6. Okay? So it doesn't say anything about the initial inventory at the beginning of week 1, right? But let's assume it's 0. Let's assume it's 0. So it's a little bit tricky because you allow inventories to carry from one week to the next, right? It's even possible that you carry the same computer you produced it in week 1, but you don't sell it until week 5. Then you have to carry like 4 weeks, right? If you carry that computer for 4 weeks, that would be $40, right? You know, you have to, you know, if you have to think about for a computer, if you have to carry how many weeks, then it's quite difficult because different computers may be carried over for different number of weeks, right? But here is a magical solution. I'm going to show you a magical solution. So those are the summary of information we had, right? For this type of problem, we can define decision variables this way. The regular production for every week, RJ, the overtime production of computers in week J, OJ. So in week 1 or week 6, you may have overtime production, right? Of course, it can be 0, but we don't know yet. So to make those decision variables. And this is the smart part. You define decision variable IJ, which is actual computers you carry over from week J to the next week. So you make the inventory at the end of week J as a decision variable. Okay? If you think about it, this is not really a decision variable, right? Once you have once you have decided RJ, the regular production level, and overtime production level, you can calculate IJ, right? So IJ is not really like an independent decision variable, right? So you don't really need this decision variable. But the problem is without these decision variables, the formulation will be very difficult. Very difficult, okay? So you can define some almost like redundant decision variables in LP, but you don't have to worry too much about that. It can be actually great news as long as you have specified all the constraints, because there is a relationship between RJ, OJ, and IJ. that's okay. You can, as long as you have specified that relationship, you will be fine. So this is what we meant. Okay. So this is like a regular production cost, right? Regular production cost. And this is the overtime production cost. And this is the holding cost. So by defining the inventory like a carryover this way, you don't have to worry how many weeks this particular computer has to be carried over. Is it 1 week or 2 weeks? If it's 2 weeks, you have times 20. If it's 3 weeks, you have the time 30, right? But you don't have to worry. I just count the inventory level at the end of each week. Okay? It may be maybe the same computer to be carried from week 2 to week 3, and then from week 3 to week 4. That doesn't matter because by doing this, that will be taken care of directly, right? And of course, the RI will be less than 160, right? Overtime will be 50 or less. Okay? So now we can also figure out the relationship between RJ, OJ, and IJ, right? And okay, so R1 production plus overtime production, that's what you produce, right? Minus I1. So I1 is the amount you carry from week 1 to week 2. So you are not using I1 to satisfy the demand of week 1, right? So you produce this much, but you don't use this many. So then it has to be 105 because you have to meet the demand exactly, right? So in week 2, you have regular production, you have overtime production. You also have the inventory carried over from week 1, so that's how many computers you have, right? But you do not produce, you do not use I2. Then you equals the demand. Okay? And similarly, you can go to week 5, right? And then in week 6, it will be a little bit different because it's the last week, right? You do not want any inventory left at the end of week 6. So you do not have, we don't have I6. I6 is 0. I6 is 0 because of the policy we want to enforce, right? We want no inventory left over at the end of week 6. Okay, so that's the constraints. I guess in this problem, right, how to define the decision variables are tricky. Yes.
I'm just wondering, with regards to constraints,
Yeah.
can we just assume that the company is reasonable and as long as RJ is less than 160, OJ is always going to be 0, or do we have to add one constraint to say that? Like OJ has to be 0 as long as RJ is less than 160? Or should we just assume
OG
that
has to be
reasonable
less than, has to be 0.
until R1 reaches 160, RJ reaches 160, right?
Okay.
So you're going to do it over time until you're full load.
That's a very good point, and that's true. That's true. Yes.
Do we assume they should be there or should be outlined as a constraint?
Well, the LP will take care of that automatically, right? Because as we know, he has 260, right?
Right.
So it's 260, the system knows we try not to give any value to the OJs, or 01, 02, 05, 06, yes. Yes. So, very good point. So that kind of has brought another interesting point, which is in LP programming, don't overthink the relationships, okay? So LP can can take care of those things by yourself. As we said, it is important to know how to define decision variables. Okay, as we said, if you do not define IGAs, then it is much more difficult to write down the constraints. Yeah. So any questions? So I have a question for you guys, okay? Here it says, the holding cost is $10, right? $10 per computer per week. What does it mean? Because every week you start with, say, 10 computers, you may end with 20 computers, right? When you say $10 per computer, what does it mean? Is it 20 or 10 or the average? You know what I'm saying? Okay.
Wouldn't this be a IJ at each particular J?
Because IGA, if you think about it, right, is what you carry from week J to week J plus 1, right, to next week. So IGA is like the end of the week inventory, right? But when you say holding, what do you mean by holding? Because within the week you have to hold, right? You have the computer on Monday, then you have to hold it until Sunday.
So it's $10 per week to hold it in inventory for future delivery. So each week you pay up front in order to use it later. So at the end of the week is when you get billed. So for I1, you get billed with $10 at the beginning of the week, so you can use it for future delivery. So in that case, it's a very clear correlation between IJ and the $10.
Mm-hmm.
So your price is 10 times IJ.
Okay. That may be good, but not always. Just give you an example. We don't have to worry about this. But suppose I have a store, right? At the beginning of this week, I have say 100 computers, right? At the end of the week, I have 200 computers. Of course, those 100 computers you begin with may be sold over the week. In the week, then you buy some new computers, right? So if you want to make the inventory cost very precise, it's kind of difficult to tell. You do have to verify for every specific computer how long you hold it. Is it 1 day or 2 days or 3 days, right? So actually, you are actually making some assumptions here. Okay? So here, you can assume that holding cost may be the case, maybe not. You may assume that the holding cost applies to the inventory level at the end of a period. Sometimes you can assume that inventory level, holding cost applies to the inventory level at the beginning of the period. And sometimes you can assume that holding cost applies to the average inventory level for the period. Okay? So all those are assumptions which may or may not be valid, in a particular situation. Okay? So if I want to write here, so we are saying that we actually made assumption here. Assumption. So holding cost applies to end of inventory Yes.
Sir, so you know the capacity computers per week is 160.
Yeah.
They have 105 computers being ordered in the first week.
Yeah.
So based on that, how do you know how much do they make? Do they make the regular 160 or do they just make the 105 to make the order?
We don't know yet. You will know that after you solve this problem. Yes. Yes.
So you just write the assumption down. Like how would you know if I were to do it at the beginning of the week or the end of the week? You know how
Yeah.
you-
So if you sometimes if it's not very clear, you can just write down your assumption and formulate the problem. Yeah. Or you can write. You can have an LP for every possible assumption. Then you compare maybe those assumptions they do not matter too much because they give you the same results.
So in an exam it would be clear.
Yeah, in the exam it will be very clear. Okay, so the next one is a transportation problem, and this problem is actually pretty simple, I would say. And actually, the next topic we are going to study is transportation. Okay, so maybe I will just skip this example. All right. Okay, so the next example is a data development analysis example. So this is a technique kind of popular in practice, okay? But the problem itself is not very, very obvious. So let's check it out. So data development analysis is, in short, DEA, is a good technique. Usually we use the DEA to compare the number of service units of the same type based on their inputs and outputs. Okay, so you want to kind of compare, say, three branches of the same bank, right? Which one is more productive than other? So of course, you cannot compare a bank with another, say, a university, right? That doesn't work because you need similar inputs, similar outputs. Here is an example about you want to evaluate three schools. Okay? Three schools, and every school you kind of find out there are three important inputs, right? So teacher to student ratio, and the funds, and the parent education level, right? And for every output, you have the reading score, you have the math score, you have history score. For example, those are the three outputs you like to evaluate, right? And you find out you have actually four schools. So Elton, Biggs, Carey, Delancey, right? So you have the inputs. So Elton, this school, input 1 is 0.06. So input 1 is the teacher-student ratio, right? And this is the fund available for student. This is the education level of the parents. Okay. For every school, you have those, same inputs, right? Different numbers, but the same inputs. And then for every school, you have three outputs, right? So this 86 is the average reading score. So reading score, math score, history score for this Elton school, right? And so on. So you have input data, you have the output data for all four schools, right? You want to see which school is more efficient than the other, right? So how do we do that? It's not very obvious, right? So someone has developed the technique called DEA, okay? So what does it do is it will ask you to define two types of decision values. Xi, which is for output, and yi, which is for input. Okay? So I is the, you have three outputs. So x1 is for the output 1, x2 is for the output 2, x3 is for output 3, right? Then you have the Y1 for input 1, input 2, input 3. For our case, that's the case, right? Sometimes you may have like 10 inputs, then you have to define Y1, Y2 up to Y10, right? So that is the decision variables, and the objective function is this. Okay. So now we're actually using this as an example. So we have 4 schools, right? We want to see which one is better, but we have to do the LP program, the DEA program for every school to figure that out. So let's try to evaluate the Delancey school. Okay, if the Delancey school is good or not, more efficient or not, compared with the 3 other schools. Okay, so that's what we want, and as we said, we want to define decision variables correspond to the output, which is x1, x2, x3. This is y1, y2, y3. So those decision variables, they are defined this way, but they do not have a very good interpretations. Okay? They do not have good interpretation. But if you must, you can say x1 is the price per unit of output 1. So y2, for example, is the price per unit of input 2. So the objective function is maximize the value of the output. Okay? So again, it's not very obvious. It's not very strict speaking, but you can interpret the objective function as the output value, the total value of the outputs. So 81 times x1 equals 81. 81 is here, right? You have 81. That is the output you have. That is the price per unit or the revenue per unit. You can interpret it this way. So 81 x1, 73 x2, 69 x3. So that is the value of the output. You want to maximize that. Okay. So let me just write here. So you want to maximize the Delancey school, right? Delancey school, Delancey's output value. Then we have some constraints. The first constraint is you try to scale. Okay, so let me go back, right? So those are the inputs, right? Inputs. So this is again the price per unit, which is not very obvious. So 0.06 times y1, that's the value of the input 1. 460 times y2, that is the value of the input 2, and so on, right? So the sum, the total input value is scaled to 1, so make it 1. Again, that's something developed by other people. We just have to follow the technique, right? And then we have 4 more constraints, okay? So the 4 more constraints means what? So let's look at this one first. So 81x1 plus 73x2 plus 69x3 look familiar? Yes, because it's in here, right? So this is the Delancey's output value, right? And this is Delancey's total input value. So as we said, that would be the input value, right? So this constraint is about Delancey, the school of Delancey, right? Delancey efficiencies. So the output cannot be more than the input. The output value cannot be more than the input value. Okay? What do you mean by that? It's actually the efficiency. Okay? Efficiency has to be less than 1%. So by doing the scaling, okay, we can say that the maximum efficiency is not the maximum efficiency is 1%. You cannot be more than that. Okay. So if the efficiency means output divided by input, right? That means output is less than input. So that's why we have this constraint. Okay. Again, it's not very intuitive, but we just have to follow the guidelines. Okay. So you have this for the Delancey school. Then you have 3 other constraints for the 3 other schools, right? All right. So you can verify. Any questions? So if I want to summarize, you basically have to remember technique. We define xi, yi this way. We have to write the objective function this way, which is to maximize the branch or the school or whatever it is, the output value. That is the objective function. And then you have you have a number of constraints. But one of them is you have to scale the school you're interested in into 1. You have to scale the input. The total value of the input is to be 1, equals 1. And then you have one constraint for each and every branch, each and every school. Okay? And it is basically output is no more than the input. And then you solve the problem. Once the objective function value is 100%, that means this school is efficient. It's more efficient than other schools. Okay? If the objective function is less than 1%, that means it's not as efficient as some other schools. So this is the DA technique. Okay? So first is like a manual science technique, but you can implement it using LP. All right? There are lots of interesting probability theories, properties of this technique, but we don't have to know those. Okay? But hopefully we can learn how to use LP to evaluate the efficiency of certain business units. Yes.
Why is the objective function only for 1 school?
Okay, so we have 4 schools here. We have to have an LP for each and every school. So here we assume we want to evaluate Delancey's efficiency. Okay, so we have this program, this LP only for Delancey school. Yes.
How would you interpret the value of the objective function? Like, what are we actually trying to maximize?
We want to maximize the output value.
Oh, okay.
Yeah.
So like what combination of inputs? Okay.
Yeah. So we can pretend that for each output there's a revenue, there's a price you can get, right? So for example, 81 is the what score is it? Is the reading score. Okay? So 81 is the reading score, which has a price x1. Okay? So 81 times x1 is the benefit you get from the reading.
And is it maximizing it for just Delancey or for all the schools?
Just for Delancey's.
Oh, okay.
We were saying that for each and every school, you have to have an LP. Okay? If you want to evaluate the efficiency of Elton's efficiency, okay, then you have to have an LP for that. And And then the objective function here would be to maximize the total output value of electrons. Yes, you have to change the objective function. All right, and if you're interested, you can kind of try to implement it using Solver, all right? Okay, so here's another example. So again, how about you guys take 2 minutes to check it out?
So how come there's a wave like it won't be
All right, so you have a machine shop, right, and which produces a single product, and that product has 3 components: component 1, component 2, and component 3. And to produce component number 1, you have to have 10 minutes on the lathe feed machine. You have to have 9 minutes on the press machine, right? And if you want to produce 1 unit of component 3, the lathe feed machine has to work for 6 minutes, and the press machine has to work 15 minutes. Okay, so that's what it means. Now it has 2 lathe feed machines and 3. You have 3 press machines. Okay, not just 1, but 2 and 3. you always split the workload evenly among the 2 lathe feed machines and evenly among the 3 press machines. Okay? So then you want to what? You want to balance the loading among the machines. Okay? So of course, the 2 lathe feed machines, they always split the work evenly, right? But you also want to make sure that the lathe feed machine will not work for too long than the press machines. You want to be balanced, right? So here says you want no machine, let's say no lathe feed machines operated more than 1 hour per day longer than any press machine. Okay, so you have press machine, you have lathe feed machine. So the time each of them works will be, the time difference cannot be more than 1 hour. Okay, could be that the lathe feed machine works longer, but not by 1 hour. Okay, and another policy is that you want to produce a quantity of components that will result in completely assembled products without any partial assemblies. Okay, so you have 3 components, right? And I guess we can assume that one final product needs 1 unit of component 1, 1 unit of component 2, and 1 unit of component 3. Okay? The objective of the firm is to maximize the number of units of finished products. Okay? So how do we do that? Obviously, you have to decide how many units of component 1, how many units of component 3, and how many units of component 2 and 3, right? So x1, x2, x3. But the objective of the firm is to maximize the number of units of finished products, right? Finished products. Now, if you have x1 units of component 1 and so on, how many finished products you can have? If you think about it, that would be the minimum of x1, x2, and x3, right? Yes?
Don't x1, x2, and x3 all have to be the same because they'll all have to be 0 at the end? So isn't it just equal to x1, x2, x3?
Yes, yes. That's a very good point, right? So if we want to use the constraint here, like the policy here, basically you have to, basically x1, x2, x3, they have to be the same, which will also be the units of finished products, right? And everything is easy, right? Everything is easy. But suppose because the point of this example is not just for this example, it is, suppose you do not have this, constraint which says, you have to have a completed assembled products without any partial assemblies. If we do not have this kind of policy or constraint, then we do have to decide on x1, x2, x3, right? Which is a more general case. If you want them to be the same, you just add a constraint which says x1 equals x2 equals x3, right? But the point I'm going to get is that if you justify x1, x2, x3 this way, right? And then you want to maximize this, right? You want to maximize this, and this is not linear, right? So in linear programming, everything has to be linear, right? You cannot maximize this because it's not linear. But there is a trick, or there is like something we want to kind of keep in mind, which is in linear programming, when you try to formulate an ALP, okay, you know, have more decision variables, sometimes even redundant decision variables, is not bad news. Oftentimes it can be good news. You know, because you know, writing down the constraints is not that difficult. To write down all the constraints, you know, sometimes even redundant, right? So the solver can figure it out, right? So in this kind of problem, we do actually have a, you know, kind of trick which is define another decision variable, which is y. So y is the quantity of assembled products, is the finished products, right? So y in general equals the minimum of x1, x2, x3, right? But if I want to come back to this particular problem, again, because we have that constraint, which makes everything much easier, right? So you can just say, because you have to make sure x1, x2, x3, then equal, which will also be the same as y, so you can have the first three constraints, right? Okay, then we have the time constraint, right? You want to produce x1 unit of component 1, you need 10 minutes, 10 times this x1 minutes of lathe machine time. Okay, so you want to produce x2 units of component 2, you need 8 times x2 minutes of lathe machine time, okay, and so on. So on the left, that is the total minutes you need, you know, you need to use the lathe machines, right? And you have 2 lathe machines, each of them can work, you know, for 80 minutes per day. So the total number of minutes you have per day is 960, right? Similarly, on the left here, those are the minutes you need. You need to use the press machines. Okay, if you want to produce x1 units of component 1, x2 units of component 2, and x3 units of component 3. Right. So on the right, it is 480 times 3 because you have 3 press machines. Okay, so now something is a little bit more tricky, which is how do we write this constraint, right? Which is no machine is operated more than 1 hour per day longer than any other machine. Okay? So this is not too easy, but here is what we can do, right? So the total minutes. The total number of minutes you need on the lathe machines divided by 2, that will be the time each lathe machine has to work, right? So the total number of minutes you need on the press machines divided by 3 will be the time you need each press machine to work, right? So each lathe machine has to work this long, each press machine has to work this long. The difference cannot be more than 1 hour, cannot be more than 60 minutes, right? So the difference between these two and its absolute value because you don't know which one is longer, right? So the absolute value of the difference is no more than 60 minutes, okay? And then you can simplify this, you have that. And this is not a linear constraint, right? Linear means plus or minus, right? You cannot have this absolute value operator here, right? So how do you transform? How do we transform this kind of constraint into something linear? Well, not that difficult. Just this one has to be less than or equal to 60, and the minus, the whole thing negative, cannot be. It has to be less than or equal to 60 as well, right? So you kind of make one constraint, make one non-linear constraint into 2 linear constraints. So any questions? Yes.
Is that bond formula supposed to be negative and then everything else in brackets, 2x?
Well, here,
Yeah. Did you say negative 2x1?
yeah, you make this negative, -2, +3, +2.
Oh, right.
Yeah, the same thing. So we have this one because we say that x1 has to be the same as x2, has to be the same as x3, right? But if we do not have that constraint, then what you can write is y has to be less than equal to x1, y has to be less than equal to x2, y has to be less than equal to x3, right? So what I'm saying is that, remember, if we do not define y, then you have to maximize this, right? Okay, so, but if you define the y, then the objective function is linear because z equals y, right? And then you can kind of translate. So what do you mean by y equals the minimum of x1, x2, and x3? Y equals the minimum of three numbers. You can translate it into something linear, which is y is less than equal to x1, y is less than equal to x2, and y has to be no more than x3. Okay? So you actually have done the translation here, right? You translate something non-linear into something linear. So that's very important because linear programming technique can only handle linear stuff. And of course, we want to, bless you, we want to see everything has to be non-negative. Okay, any questions? All right, so how about we take a 5-minute break and we are going to the next topic, which is about transportation. Thank you very much.